Arenes are aromatic hydrocarbons containing one or more benzene rings. The strict chemical definition of what makes a compound aromatic is not required for A-level chemistry, but the term aromatic is derived from the Latin word aroma, meaning fragrance. However, it should be noted that some aromatic compounds are in fact odourless. The history for the discovery of the structure of benzene is an interesting one, and is typical of how scientific theories evolve in the light of experimental evidence available at the time. As early as 1825, Michael Faraday determined the empirical formula of benzene to be CH. Soon after, it was confirmed that the molecular formula was C6H6. It was suspected that owing to the high carbon-to-hydrogen ratio, that benzene was an unsaturated compound. That is, it contained carbon-to-carbon multiple bonds, and was a linear structure. However, benzene does not undergo the electrophilic addition reactions typical of other alkenes. It does not discolour bromine water, for example, which is a test for unsaturation. In 1865, a German chemist called Kekulé suggested that benzene might be a ring structure with alternating double bonds, and he proposed a structure that we would call cyclohexa-1,3,5-triene. However, this structure still did not answer the question as to why benzene did not undergo typical electrophilic addition reactions of alkenes. Also, if we look at the enthalpy of hydrogenation of cyclohexene, that is, when we add hydrogen onto cyclohexene to produce cyclohexane, the reaction is exothermic, and 120 kilojoules per mole of energy is released, showing that the cyclohexene structure is less stable than cyclohexane. For Kekulé's proposed structure of cyclohexa-1,3,5-triene, you would expect 3 times the amount of energy to be released when it is hydrogenated, as there are 3 times as many double bonds. You would expect 360 kilojoules per mole of energy to be released. However, when benzene is hydrogenated, it only releases 208 kilojoules per mole, suggesting that the benzene structure is more stable than the cyclic alkene structure proposed by Kekulé. In 1922, Kathleen Lonsdale, a chemist from University College London, used a technique of X-ray diffraction on a crystal of hexachlorobenzene. With X-ray diffraction, you fire a beam of X-rays at a crystal structure, and these X-rays are diffracted and will make patterns depending on the position of the atoms in the molecule. By examining the patterns made by the diffracted X-rays, and by applying some very clever calculations, it is possible to work back and discover the positioning of the atoms that cause the patterns. By doing this, Lonsdale confirmed that the benzene molecule was flat, that all the bond angles were 120 degrees, and, importantly, the carbon-to-carbon bond lengths were all the same. As a result of these findings, the resonance model was developed, which accounted for the experimental evidence. With the resonance model of benzene, there are 6 carbon atoms in a ring, and 3 electrons from the outer shell of each carbon are used to form sigma bonds between 2 other carbon atoms and 1 hydrogen atom by direct overlap of orbitals. This then leaves a p orbital with lobes above and below the plane of the molecule. The lobes of the p orbitals merge above and below the plane of the molecule to produce pi clouds, where the 6 electrons are delocalized, meaning the electrons from the p orbitals are shared throughout the entire ring, rather than just being shared in pairs between 2 carbon atoms, as they would be in a normal carbon-to-carbon double bond. The resonance model explains why benzene does not undergo the typical electrophilic addition reactions of alkenes, as there are no high electron density carbon-to-carbon double bonds present that electrophiles can attack. It also explains why the enthalpy of hydrogenation is lower than that expected for the Kekulé structure, since the delocalization of electrons leads to a much more stable molecule which is lower in enthalpy. The difference between the enthalpy change expected for the hydrogenation of the Kekulé structure and that observed for the benzene molecule is called the delocalization energy, or resonance energy.